Problem we're going to look at today is problem 8.25 out of Fundamentals of Heat and Mass Transfer by Bergman and Levine. Problem is stated as follows. It says that engine oil is heated by flowing through a circular tube of diameter d is equal to 50 millimeters and a length equal to 25 millimeters, or 25 meters, and whose surface is maintained at a temperature of 150 degrees C. We're asked in the first problem if the flow rate and inlet temperature of the oil are 0.5 kilogram per second at 20 degrees C, what is the outlet temperature or the mean outlet temperature of TMO, and what is the total heat transfer rate Q for the tube? And then in the second question, we're asked for flow rates ranging from 0.5 to 2 kilogram per second. We're asked to compute and plot the variations of the outlet temperature and Q with M. And then it asks for what flow rates are Q, which is the heat flux, and Tm, which is the outlet temperature, maximize. And we need to explain our results. So decomposing the problem, we can look up in the appendix the engine oil properties, which are given as follows. And we're also given the hydraulic diameter, which is just equal to the diameter of the pipe, which is 0.05 meters. We know our mass flow rate for the first problem is 0.5 kilogram per second. Our inlet temperature is 20 degrees Celsius, and our external temperature is fixed on the pipe at 150 degrees C. And we also know that the length of the pipe is 25 meters. And so in the first problem, we want to find the total heat rate Q as well as the outlet temperature. And then in the second problem, we need to plot Q and the outlet temperature and find where each of them are maximum. Looking at a schematic, we have our pipe here, again, diameter of 50 millimeters, our inlet flow at 20 degrees C and half a kilogram per second, and our surface temperature of 150 degrees C. Some assumptions we're going to make, we're going to assume that the material properties are constant as the oil is changing temperature. We're going to assume that the temperature of 150 degrees C is fixed across the entire tube. We're going to neglect radiation from the tube. And we're also going to neglect conduction through the pipe wall. So we're going to assume that the inner surface is going to maintain that 150 degrees C. And we're also going to evaluate all of our fluid properties at the inlet temperature of 20 degrees Celsius. So for our first calculation, the first thing we're going to do is find our velocity by taking our mass flow rate of 0.5 over rho A, A being the cross-sectional area. And we find that our approximate flow rate is about 0.28612 meters per second. We can then use that to calculate the Reynolds number and determine if the flow is going to be turbulent or laminar. In this case, our Reynolds number is quite low at 12.745. The critical Reynolds number in pipe flow is around 2300, so we can be pretty confident that our flow is going to be laminar. And since our flow is going to be laminar, we can use this empirical correlation for a laminar fully developed pipe with a uniform surface temperature, and the Nusselt number is actually going to be fixed at about 3.66. We can then take that Nusselt number to calculate the average heat transfer coefficient across the pipe by taking the Nusselt number times the thermal conductivity of the fluid divided by the hydraulic diameter of the pipe. And that's going to give us a heat transfer coefficient of approximately 10.614 watts per meter squared Kelvin. We can then use this correlation, which is going to be in the difference between the surface temperature and the outlet temperature over the difference of the surface temperature and the inlet temperature, which is equal to the exponent of the surface area of the inside of the pipe times our heat transfer coefficient over our mass flow rate times our specific heat of the fluid. And we can actually take that equation and rearrange it to solve for our mean outlet temperature. And the rearranged equation will look like this. And when we plug in all of our numbers, we get a value of about 25.67 degrees Celsius at the outlet temperature. So about a 5.67 degree rise from the inlet. Then to calculate our heat flux, we take this equation, which is Q, H bar being our average heat transfer coefficient that we calculated, AS being, again, the surface area on the inside of the pipe. And we're going to use this new term, which is delta TLM, which is the log mean temperature of our pipe. And we can calculate delta TLM as this equation. So again, the difference between the surface and the outlet, the difference between the surface and the inlet, over the natural log of those two differences. And we're going to use our calculated outlet temperature of 25.67 degrees, plug that in, and we'll get a log mean temperature of about 127.142 degrees Celsius. Plugging that into the previous equation, we will get a value of about 5,299 watts of total energy dissipated by the fluid moving through the pipe. So for calculation B, we're actually going to do this in MATLAB. So we're asked to find the mean outlet temperature as well as the total heat transfer rate as a function of the mass flow rate through the pipe. So just a simple MATLAB code here. We start by defining all of our material properties as well as our parameters that were given in the problem. We're just quickly going to calculate both the area of the cross section of the pipe as well as our surface area, which is going to be pi dl. And then we'll define a line space for our mass flow rate. So we're asked to go from a mass flow rate of 0.5 to 2, and we're going to take that over 100 data points. So it'll do a linear interpolation of 100 data points between 0.5 and 0.2 using the line space. We can then calculate our velocity at all of these flow rates as before, and then get an H value for all of those flow rates. We can then go ahead and calculate our temperature outlet with the same equation that we used before, as well as our log mean temperature with the previous equation. And finally, plug in that log mean temperature into our equation for the heat transfer rate. And we'll just go through this simple plotting scheme to plot these two plots. And so what we can see is that it's actually an inverse relationship if we want to maximize both the mean outlet temperature as well as the total heat transfer rate. And essentially what that means is that low flow rates, our fluid is moving relatively slow through the pipe, which means the temperature rise is going to be quite a lot. So we get that temperature rise of about 25.67 at the flow rate of half a meter per second, half a kilogram per second. And as our mass flow rate increases, our temperature is actually going to drop since the fluid is moving quite fast through the pipe and does not have time to pick up a lot of thermal energy from that surface temperature. The total mass flow rate is actually going to be the other way around, where as we increase our flow rate, our heat transfer rate is actually going to increase. And you can see both our temperature is decreasing and our mass flow rate is increasing, and they're both approaching an asymptotic point. And that asymptote is essentially going to be where the outlet temperature is going to be equal to the inlet temperature. And at that point, we're actually not going to transfer any more energy through that fluid, and we're going to achieve our maximum heat transfer rate.